So this is question 24, sorry, page 24, question 9. So we've got women and men, and they either use a stick or don't use a stick. So it didn't really matter which way you did it. You might have done yours rotated through 90 degrees. But we've got 63 women and 47 men, so that's a total of 110 people. And 18 of the men use a walking stick, so that means 29 don't. And 26 of the women do. So that is 37. And so that means we've got 44 there and 66 there. And we are asked firstly, what's the probability that someone picks at random, uses a stick? So we've got 110 people altogether, and 44 of them do, which simplifies. Annoyingly, in this book, they tend to, oh no, this one they've left it as fractions. They sometimes tend to use decimals rather than fractions. But then we get into the given ones. So do you remember we talked about numerator and denominator? And it almost sort of looks a bit fractiony, doesn't it? The way it's drawn. It's sort of, so probability that they use a stick given that they are female. So we're saying, right, this is my denominator. We're only interested in the female members. So there are 63 of them. Of those members, only those 63 we're interested in. How many of them use a stick? 26 out of 63. So it wasn't 44 out of 63. It was of the given people, we've definitely chosen a woman. What proportion of them use a stick? It's 26 out of 63. And then similarly, this was sort of the other way round. What's the probability someone's male given that they use a stick? So this time we are only interested in these 44 people. So we know we've chosen someone who uses a stick. That's what that's telling us. So we've only got 44 people to choose from. How many of those 44 people are male? That was 18. So this is conditional probability, and you can tell, normally you can tell with a conditional probability question because it uses that key phrase, given that. We're being told something has happened and we're asked something based on that. So we did a couple of two-way table questions. So what about Venn diagram questions? Well, if we stay on page 24 and have a look at this question. So firstly, again, I'm very happy if people use whiteboards. They are not draw. But yeah, see if you can knock up a Venn diagram for this question. And then we're asked 3 given that questions of varying difficulty. So this is just the same as the second half of the last lesson, it's just we are applying it to Venn diagrams rather than two-way tables. remember the 0.55 for A includes the bit in the middle. And don't forget the bit outside the circles, which we have to work out in this case. So remember, with the given thing, the right-hand side of the given sign will give you a denominator, left-hand side the numerator. So the probability of A, given that B has happened. So B has happened, and the chance of that, we're not dealing now with the number of people like we were with our two-way tables. Now we're dealing with the probability, but it works the same. So we're not putting the number of people who have sticks or a men or whatever. We're dealing now with the probability of B, which is 0.4. Of that probability, what part is down to A? So here's our B probability, 0.4. This is the bit which is down to A. So it's 0.15 out of 0.4, and that simplifies to 3/8, but your calculator would do that for you. So it is, what's the probability of B? That goes on our denominator. And of that probability of B, which bit is also A? So this is the probability of A intersection B, isn't it? In fact, we could write a formal sort of rule for this. The probability of A given B, well, the probability of B goes on our denominator, and our numerator is the intersection between A and B. Now, we will do one question later where you need that rule. That rule is sort of often, it's often stated in revision guides, it's on the syllabus. I don't think we ever actually need it, apart from very, very rare situations. So here, the probability of A union B, that's this, it's 0.8. So that goes on my denominator. Of that, how much of that is down to B? 0.4. So that's a half. So what they're basically saying there is, if A or B happens, what's the probability that actually it's B that's happened? Well, B is half of the overall probability, so that's a half. And here, what's the probability that B hasn't happened? Well, that's 0.6. Of that, which bit is also A not happening? Now again, it's not the probability of A not happening, it's the probability of A not happening intersection with B not happening. So it's just this bit here. So that's 0.2 out of 0.6, which is equivalent. So it's a little bit hard to get your head around because some of these are so sort of obscure. But given that, problems, split it into numerator and denominator. do the denominator first and then think of that probability, which part is down to the numerator. So I just put a couple of questions up, but again, as always, we probably won't get through them all, so I suggest I encourage you to finish them independently.
Can I just pop the list?
Yes, sure. And I'll put page 27, 9 and 12 down, but I suspect there'll be ones that you do independently. It's this one where they annoyingly use So A union B is just everything in the circle, so that's 0.7. So the probability of A given B. So what that means is B has happened. B has happened. So that's my denominator. It's like when you roll a dice, there are 6 things that can happen, but it might say you've only rolled an odd number, so you're down to 3 things. We're only down to those possibilities. So we've got 0.4, that's my denominator. Of that, so I'm only looking now, I'm blinkered, I'm only looking at that share. Which bit of that is also A? That's my numerator. And that is 0.3. In C, A hasn't happened. Given that A hasn't happened, so what we're talking about is that. So that's 0.58. So that's my denominator. Just like if you say we roll a dice and it's an odd number, we know our denominator is 3. Our denominator here is 0.58. Of that, what part is B? Well, the part of that which is B is this bit, 0.28. So it's 0.28 out of 0.58, which cancels down as a decimal to that. And then the last one, given that A or B has happened. So we're only looking inside the circles. So our denominator is 0.7. What's the probability that B happens? So what part of that green shaded area is B? That's 0.4, which is 4/7. Why on earth they chose to write that? And 0.517 rounded, I do not know. But that's it. That's it. Just give me a few more minutes. So with number 2, we've got the Venn diagram. The probability of the probability of D happening is 0.4. Given that that's happened, what's probability C happens? Well, so I'm saying that's the same as saying what proportion of D is C. It's 0.25 out of 0.4, so that simplifies down to 625. This is the reverse. C has happened, 0.8. What part of that is down to D? 0.25 out of 0.8. And I shaded the diagram for the last one. C hasn't happened, so that's the green area, 0.2. Of that, what part is down to D not happening? 0.05. Now, if you got on to question 11, well done. I'm going to just put the answer to that one up, but encourage you to. Actually, no. I'll tell you what. No, I'll give you a couple more minutes. If you're off question 11, then have a go at 9 and 12. But yeah, in a couple more minutes we'll have a go at that one. It's worth doing. This is a bit algebraic, isn't it? We know how much they like the algebra. The first thing I would write down is what I know x plus y have to add up to. What x and y have to add up to. Quite a clever question, this. So, Jodie, with this question 11, what do we know about x and y together?
They add up to 1.7.
Fantastic. And we're told that A given B is the same as the probability of B not happening. The probability of B not happening is 0.3. But I can work out the probability of A given B using my normal approach. This is the probability of B on the denominator, and of that, what part is down to A in the numerator? Well, the probability of B is x plus y. But we know what that is, don't we? We know that's 0.7. Of that, which part of that probability of B is also A? And the question tells us that's the same as 0.3. It's the same as B not happening. So a little bit of algebra, multiply both sides by 0.7, and we get x is 0.21, and therefore, as they have to add up to 0.7, y is 0.49. And I strongly encourage you to have a go at those two as well. But I would like to move on. So my next question is, well, firstly I'm going to make an observation. Every question we've done so far, apart from this one I suppose, we've known the overlap, we've known the intersection, and that makes it a whole lot easier to draw the Venn diagram. What if we don't know the intersection? So that's my next step. What if we don't know the intersection? Now we don't know in this question, we're not told in this question if A and B are mutually exclusive, but I know they can't be mutually exclusive because their probabilities add up to more than one. So there must be an overlap. There must be an overlap. I'm told what A union B is, but I'm not told what A intersection B is. So it's not quite as easy as normal to knock up the Venn diagram. However, I'm hoping that some of you would be able to use what I would say is sort of a common sense approach to work it out. Because together, 0.6 and 0.7 make 1.3, but actually we're told that together they're 0.9. So I'm hoping you'll be able to work out what that means the intersection has to be. But let's imagine you don't. So there is an equation which we can use. And it's a sort of common sense equation really, but it's stated on the syllabus, and that is that if you've got two events like this, the probability of A union B is equal to, so the area of both circles, it's equal to the probability of A, the area of A, plus the probability of B, the area of B, but of course if I do that I've counted this bit in the middle twice. So that is one of two probability equations that we could potentially need to use if common sense lets us down. And all that rule is a statement of what we can see from the picture, that the total area of A and B is equal to the A circle plus the B circle, but that means I've counted that bit in the middle twice, so I have to take that away. So if we apply that to this problem, we've got 0.9 is A union B, A is 0.6, B 0.7, and the intersection is the bit that we don't know. So hopefully you can see therefore that the intersection has to be 0.4, which you may well have been able to see anyway. That was how much bigger the probability of A and the probability of B was than the probability of A union B. Now we're off to the races, because the probability of A is 0.6, so I need to put a 0.2 there. Probability of B 0.7, so that's going to be a 0.3. Altogether there, I've got 0.9. And in terms of the question, I found A union B, A intersection B was 0.4. So that's one scenario where we're not given the intersection, but we can work it out, and it may be that this formula is something you choose to remember, or it may be that you just rely on common sense. I'll get you to practice one of those in just a moment. Let's look at a different example where we don't know the intersection. I note here that it doesn't mention a Venn diagram at all. But two events, I'm going to draw a Venn diagram. I'm always going to draw a Venn diagram for these sorts of questions because I can't visualise it without the Venn diagram. And again, I don't know the intersection. So I'm a little bit at a loss. I could write in 0.2 and 0.6, but I'd only have to rub them out because it might be wrong. There might be no overlaps, they might be mutually exclusive. So we're told the probability of C given D, which I know in my diagram I get by working out the probability of D, that goes in my denominator, and I'm interested in what part of that is down to C. So it's this bit here, which is the probability of C intersection D. And that's the second of the two probability formula which we could use to help us solve problems. So the probability of C, given that D has happened, so that's my denominator, the probability of D, and I normally use words of that, which part is also C, so what we're saying is that's C intersection D on the top. And I think that in almost every situation you can avoid having to do that, you can use common sense, unless they throw you a bit of a curveball here. So if I look at this example, well, I'll tell you what, why don't you try and plug the numbers in and work out. Remember, what we're trying to do is work out the overlap. We're trying to work out this. So this tells me the overlap is 0.18. If I just multiply both sides by 0.6, and then I can fill in the rest. That's 0.02. That needs to add up to 0.6, so that's 0.42, and 0.38, is that? 0.6, 0.62, yes. Now, we've met that already. I mentioned it earlier. I'm not a huge fan of formula where common sense can be used as an alternative, but actually, those are two examples. So if I just get you to do two more examples along those lines, both on page 29, questions 6 and 7. So one is an example of one, and one is an example of the other. So we're using those formula to solve problems, unless we can kick in with our good old common sense. And then question 9 after that. I'm not sure you need a formula for question 9, but that's another good one to try. Again, no mention of a Venn diagram, but I'm drawing a Venn diagram here. And in order to draw the Venn diagram, I need to know the overlap. So working out my overlap is the first thing I'm going to do. So I was given A given B, so I wrote the formula for A given B, plugged in what I knew and used that to work out the intersection. Then I'm off to the races, I can draw my Venn diagram. B hasn't happened. I get 0.6. Am I missing something? I'm getting 0.6 for B. I get 0.3 over 0.5.
Why are you doing it like that? It's just not a...
Oh, I'm being stupid, aren't I? Yes, sorry, it's not A and not B, so it's outside the circle, isn't it? It's not, sorry, it's not even a given question, is it? Thank you. Yeah, yes, that's a really good point, actually. One of those, my many mistakes that I'm quite pleased I made. Yeah, because that one isn't a given question at all. So that, so this one is a given question, so that is probability of A. But yeah, that's just outside both circles, not A happening and not B happening. And that is inside B and not inside A, so that's 0.3. And this uses the first of those two rules that we talked about. I changed all my fractions to 20ths when I did this one. So don't feel you have to use the formula. If you note that probability of A and probability of B add up to 15/20ths, but the overall circle is only 12/20ths, and therefore that means that the overlap has to be 3/20ths, then that's brilliant. And if the overlap is 3/20ths, that means that this is 2/20ths. I'm going to leave it as 20ths because I can cancel any final answers. And probability of B is 10/20ths, so that's 7/20ths. I've got 12/20ths there, so that's 8/20ths.
So if the question's in fractions, can you still do it in decimals?
Yes, you can. Yeah. In fact, I think, yeah, this one maybe. So I won't make the same mistake again. I've only got one given that question here. So that's the probability of B, which is a half. That's on the bottom. And of that, which bit is down to A? 3/20ths. divide that out, you get 0.3. This is the overlap between B and A not happening, so that's 7/20. And this is the overlap between A not happening and B not happening, which is just this bit outside. 8/20ths, which of course becomes 0.4. I would strongly encourage you, if you hadn't had a go at question 9, to do that one. However, question 9, they give you the intersection. So I reckon question 9, you don't need to worry about either of those rules, but it's still a really good one to try. And then we'll start next lesson with another one before moving on to tree diagrams, which we will finish next lesson. Now, the reason I'm focusing on Venn diagrams rather than doing a lot more on tree diagrams is because of what it says in the pre-release. So these 3 lessons that we're spending are mentioned here, and it's pretty certain it'll be a Venn diagram question. That doesn't mean they can't throw in a tree diagram. You know, we're told very clearly that, you know, generic skills, and you can argue that a tree diagram is a generic skill, will feature elsewhere, but that's that. And of course, the good news about doing this quite recently is that we probably don't need to spend a lot of time revising it.